I just saw people doing it.
I've been ice skating one time in the last
All right. Good afternoon.
Yeah, I was trying to teach me.
Today we are talking about fatigue concentration factor. Then I'm gonna go over one example to cover whatever we talked about that on fatigue so far. So let's. Yes.
Can you post the home solution?
Yeah, homework. I can do that. So if we have if we have a mechanical component like this, suppose it's part of a driving shaft with a different diameter. Here is the diameter is 2 inch, and here we have 3 inch. Suppose it's under bending moment of 1,000 pound each. Pure bending moment is applied to this mechanical component. If I ask you do the stress analysis for this, first you need to find the critical section if the shaft is not moving. So we don't have any rotation on the shaft. You should find which section is gonna see the maximum stress. So the only load that you can see here, it's a bending moment. So the bending moment, it's gonna be the same in each section on this shaft. So it's gonna be 1,000 pounds. So it's gonna tell me the stress is gonna be the maximum at the smaller parts of the shaft, which is gonna be this side. So any section on the smaller parts of the shaft can be the critical section. I can find how a normal stress is going to be 32 MC divided by I, which is going to be 32 times M divided by pi t power 3. 32 times 1,000 pi d power 3. It's going to be 2 power 3. Uh, 1273 psi. It's going to be the stress applied in any section on the smaller side of the this component. So now, if this mechanical component starts rotating, so then due to the rotation, we are going to have fatigue. We need to do the fatigue analysis. So since we have this continuity on the cross section, we are going from 2 inch to 3 inch. We have this continuity here. Then fatigue stress concentration factor is gonna show up, which we label it as a KF. Whatever is the KF, we should multiply that by this sigma that we got from the static analysis. and come out with the new stress due to the fatigue analysis. So this is how the fatigue concentration factor is going to show up on the analysis on fatigue problem. Fatigue concentration factor is a function of KT. KT, if you remember, it was static stress concentration factor. Table A15. Depending on the geometry of component and the loading, you can find KT. What is the Q? Q, we call it notch sensitivity. Q is a notch sensitivity, is representing the sensitivity of Kf to the stress concentration factor. Fully sensitive, if you have a material with a fully sensitive, Q is going to be 1, then Kf is going to be equal to Kt. Q equals to 1 times Kt minus 1 and 1 can be cancelled out, and Kf is going to be equal to Kt. Zero sensitive, Q equals to 0, Kf is going to be 1. Q equals to 0, Kf equals to 1 times 1273, you don't see any effect of concentration factor under stress. So I will look at the value of the Q and KT for this problem, then we can work on one example. So suppose, the radius of the fillet that we have here has a radius of 0.1 inch. Suppose these are the information that I provide. And it's made of the material with the ultimate strength of 150 kPSI. So these are the information that so the first thing that I need to find is KT. So look at the table A15 on the back of the book and find the mechanical components and the loading which is similar to this one. So table A15-9 has this component with a circular cross section which is under pure bending moment. The other one is the same thing like this, but the load is going to be the torsion. So for this one, you can read the value for KT. To find KT first, you need to find this value, which is R, the radius of the fillet divided by the diameter of the smaller component. So R divided by the smaller diameter is going to be 0.1 divided by 2 inch is going to be 0.05. So 0.05, it's going to be somewhere here. So now, depending on the ratio between D and uppercase and the lowercase of the D, I can find the KT. 3 divided by 2 is going to be 1.5. It's going to be this line. So 0.05 go up somewhere here. 1.8, 2.2, about 2. I read KT as a 2. So if you read 2.1, 2.2, that's fine. I mean, it's because we are just reading from the vertical axis, so you might say I can read 2.1. A59 KT equals to 2. Now, I need to find notch sensitivity, that I will talk about that. There are two ways that you can find Q. One is looking at this figure 620. Whatever is the notch radius in inch, in this case R is 0.1 inch, somewhere here. And depending on the ultimate strength of the material, find the value for Q. 0.1, it's 150 kpsi, it's going to be somewhere here. 0.1 is coming up. It's about 0.9. Figure 620. This is how I can find Q. If the notch radius in millimeter, you can look at the numbers on the top and find the corresponding Q. Now I have everything to find Kf. Kf would be 1 plus Q 0.9 KT2 minus 1. It's going to be 1 plus 0.9 times 1, or 1.9. So this 1.9 is going to be multiplied by 1273. It's gonna increase the stress by about factor of 2. So if you did your design based on this stress, then you are gonna see failure if the mechanical component is rotated, because the fatigue concentration factor is gonna increase the stress, then you have a fatigue issue. Can you see that? So this is one way that you can find Q. When we have shear stress, suppose instead of bending moment we have shear stress, torque. If it was torque, the torque is making shear stress, then shear stress is instead of having KT, you are going to have KTS, shear stress. And instead of having KF, you are going to have KFS. KFS is going to be 1 plus Q is going to change to QS. Notch sensitivity for shear times KTS minus 1. So if you are looking for QS, then you should look at this figure, 621. This is notch sensitivity for shear. It's gonna be similar to the figure 620, but with different numbers. So it's slightly different at Q. So make sure that you are using the correct value for Q. There is alternative to find Q. If you don't like to look at that figure 620, you can use this equation. Q equals to 1 divided by 1 plus square root of A divided by square root of R. R is the radius of the fillet that you can measure or you are given. But what would be the A? The square root of A, if you have bending or axial loading, can be obtained by this equation. If you have torsion, it's coming from this equation. So this is your option to pick. Either by going figure 620 or 621, or by picking these two equations and plugging on equation 634. So it's going to be more accurate because you calculate that the other one, there should be a slight error already in the numbers. Any questions so far? All right. Let me work on one example. The example would be on the lecture, so I'm just rewriting this on the board, but you can find the example on the lecture. Alright. There is a rotating shaft which is simply supported at point A and B. Let me draw the shaft. So this is the shaft that we have. It has a smaller diameter, larger diameter, and another, the last part, which is going to be this part, is mounted on these two ball bearings. So these two ball bearings they're gonna support the shaft while it's rotating. So it's mounted on this ball bearing. They represented the ball bearing. It's simply supported. Just imagine like this. They are rotating about these two bearings. So the dimensions would be from point A to B. (250 millimeter). One load with the magnitude of 6.8 kilonewton applied at this location, which has a distance of 75 millimeter from point B. Let me call it point E. From here to here is 100 millimeter. Point C, and this is point D, which is 125 millimeter. It's made of, the material is AISI 1050 cold draft. So the material of the shaft is given, the load is given. The question is after how many cycles we are gonna see the failure if it occurs. So how many times this shaft is running before failure occurs. So the only load that I have here is this vertical force or load that I have here. It's making bending moment over this shaft. So if I draw the bending moment diagram for this shaft, it's gonna look like this. Point E, this is point E, point B, point C, point P, and point A. First, I need to find the reactions here, then I can draw this bending moment diagram. So the reactions would be in the opposite direction, R, A, and R, D. RA plus RD should be equals to 6.8 kilonewton. Also, bending moment either at point A or at point B should be 0. These two equations is going to give me RA equals to 2.78 kilonewton and RD equals to 4.018 kilonewton. I just skipped this equation. I didn't write it down, but you can write the bending moment at point A and set it equals to 0. Two equations, two unknowns, solve for RA and RB. Now, can you tell me which section or which point is going to be the critical section? D, B, you said. Okay, B. Section B or point B. I mean, when I say point, I mean the section B. So any different thought?
Could be C.
C, why is that?
Because it's another small diameter and it has a stress concentration thing right there.
Section C. Why not section B? I mean, because section B also is going to see the stress concentration, section B. And it's a smaller component, but we don't know how much would be the bending moment to compare B and C. Another section that you should study is section E, because section E is gonna see the largest bending moment, and you don't know how much stress is gonna develop at section E comparing to the stress developed at section B and C. So we are gonna have 3 candidates, and why 3? Because section B is gonna be the smallest diameter, and this section is gonna have the greatest moment for this portion. So section B should be studied. Section E should be studied because it's gonna have the greatest bending moment. And section C also should be studied because we should find what would be the bending moment applied to that, and then see which one is gonna develop the greater stress. So I'm gonna find bending moment at these 3 points. At point B, M at point C, and M at point E. And then by knowing this, I can find the stress at each section and then continue the process. So M at point B, which is going to be this one, this load times this distance, it's going to give me this 2.782 times 250 millimeter is going to be 695.5 Newton meter. At point C, how can I find bending moment at point C? Either by multiplying this to this distance or multiplying this force times this distance minus this force times this distance. So either way, we will get the same result. We have covered this on the beams. So 2.782 times this distance, 250 plus 175, 325, 425 minus this force times this distance, which is 6.8. I forgot to add Newton. It should change to the Newton, not kilonewton. I will get 904.15, and point E is gonna have 502. Sorry, 502. And point E is gonna have the greatest bending moment, which is 2.782 kilonewton times the distance, which is 325. 904.15. Next step is finding the stress at point B, C, and E. I have the bending moment applied to point B, and sigma at B would be 32 M pi E power 3. B for section B. 32 MB is 695.5. Pi diameter is, this is 32 millimeter, this is 35 millimeter, and this is 38. We have 32 millimeter. (216 megapascal). It's a normal stress applied to section B. For section C or E, let's start with E. 32 times bending moment is 904. Diameter is 38. It's a largest diameter. It's 167.8 megapascal. And sigma or normal stress at point C 35. The diameter is 35, bending moment is 502. I get 119 megapascal.
Dr. Duffy,
Yes.
so for the moment at C, should it be 2.782 times 325? 10 to the negative third?
For C,
Yeah.
2 points, point C. This is point C. 250 plus 175. It's gonna be 425.
Okay, never mind.
325 is gonna be for this part.
Yeah, okay, never mind.
Yeah. So 216 is for this cross section with discontinuity. 167 is for this cross section with no discontinuity, and this one is 119 for this section with the discontinuity. The stress concentration factor doesn't have any effect on this one because we don't have any discontinuity here, so this value is going to be the same for the fatigue stress. But these two might change and they are going to increase. So either this section or this one would be the candidates for the critical section. We will answer this question shortly. But depending on the size, you might get a larger number for section E than the other ones, but you have to check the fatigue concentration factor to see what would be the greatest stress after considering the stress concentration. Any questions so far? Next thing that I'm gonna do is, let me keep these three. I'm gonna get rid of these parts and try to find fatigue concentration factor. I will start with section B. At B, this section. This component that I have is something like this. It's on the moment, there is no other load applied to that. I mean, we are looking at the bending moment. We have two different diameter. We are looking for KF at this section. So first thing that I need to find is KT, because we know that KF would be 1 plus Q times KT minus 1. I need to find Q and KT for section B. KT. I need to find D over D. D over D is 38 divided by 32. It's 1.118, and this radius is 3 millimeters. The radius of the fillet is given 3 millimeters. R divided by 2 is 3 divided by 32 is 0.09. So R over D is 0.09. This is 0.1, just slightly before 0.1. Which curve we should pick? 1.18. We have 1.1. This is 1.5. I mean, I can assume 1.1 is going to be similar to this. 0.9 coming up. This is 1.1. Look at this, it's 1.4, the middle is gonna be 1.6. I read 1.65. So you can if you're at 1.68, that's fine. If you're at 1.63, that's fine. So Q, we find KT, we are gonna find Q. So we have bending moment, so we need to find Q, not QS. What would be the notch radius in inch? Here I have in millimeter. It's a 3 millimeter, so I'm using this line. So 3 millimeter, what would be the S ultimate? The material is given, table A20. For this one, S ultimate is 690 megapascal, and S yield is 580 megapascal. 500 and 690. 690, it's about 0.7 gigapascal. 100 kpsi, it's same as 700 megapascal. So 700 megapascal and 3, it's coming here. If we read this, 0.8 is here, 0.9 is here, I give it 0.83 or 2. Again, you can have some error on reading the numbers, but it should be around 0.8. Now I can find KF. KF would be 1 plus 0.82. KT 1.65 minus 1, I will get 1.53. This is KF. At point C, I need to find, just repeat the same process except with a different diameter for the smaller component. D over D would be 38 divided by, here we have 32, now we are going to have 35, 1.08, 5. R over D would be 3 divided by 35, 0.08. I can read KT is about 1.6. Q would be the same because the notch is going to be still 3 millimeter, and the material would be the same. So Q is 0.82. KF would be 1.49. Now I make this table points, the critical, I'm gonna have all 3 critical sections, candidates for critical section here, just to show you what should be the process. But we know that point E is out of the picture, so we don't look at point E because there is no fatigue concentration factor, and it has a smaller number than the other, than these two. So, but let me write points D, point E, and point C. The sigma that I got for point D was 260. For point E was 167, and for point C is 190. Fatigue concentration factor for section B is 1.53. For point E is 1, is not increasing. For point C is 1.49. So sigma max, this times this, 330.48. KF 330.48, 167.8. Here, this one was 119. It's significantly less than this, but if I multiply this to this one, I will get 177.3, which is greater than section B. Now you can decide about the critical section, which is section B. For the rest of the process, I'm looking at section B. Any questions so far? Now, what I need to do is, I'm looking at this. If 330.48 is greater than SE, endurance limit. If the stress is greater than this, we have finite life. But if it's less than SE, this shaft is running forever with no failure. So I need to find the endurance limit. Endurance limit is KA, KB, KC, KB, KE, KF times S squared. Last year final exam, there was, I think there were 2 or 3 problems. One of them was designing from scratch. So just something like this. It covers everything. I can ask all topics that we cover by giving something like this. And you go step by step to finish it, the process. So let me move on this. KF. This KF is different than this KF. I mean, don't be confused. That KF is fatigue concentration factor. This one is the modification factor for endurance limit. It's totally different. So don't use this on this one. So KA. KA was surface. This shaft has been machined, so if I want to find the surface finish factor, then I should look at table 6.2. Ka would be A, which is 4.51. Machine A in ultimate in megapascal 4.51 times S ultimate, which is 690. Don't change it to Pascal. It should be in megapascal. Power negative 0.265. You will get 0.798. KB, size factor. size factor has, you should be careful when you are using equation 620. It's applied for the round and rotating diameter and for bending and for torsion loads. So if you have axial load, KB is going to be 1. If you have bending moment, bending load, it's a round and the shaft is rotating. So we are going to use this equation. It's in millimeter. We are going to, in millimeter, we are going to use this equation. So the diameter is less than 51. So we are going to use 1.24 times D, which is 32. Don't change it to meter. It should be millimeter. 32. These are the points or mistake that I have seen. Negative 0.107. Don't change it to the meter unit. So you will get 0.858. Kc is the load factor. For the bending, we have 1. Kd is a temperature. It's not talking about the temperature, so I can assume equals to 1. And reliability, it doesn't talk about reliability, you can assume it's 1. And the other factor, it doesn't talk about the other factor, so we can assume 1. So now, aspirin E is half of S ultimate for S ultimate less than 1400 megapascal, which is the Kc. Aspirin E is going to be half of 690, which is 385 megapascal. Now find SE. SE would be 0.798, 0.858, Kc is 1, E is 1, and aspirin is 395. If you multiply
340.
Thank you. On that. So it's going to be 236. So as you see, the factor modified the aspirin E from 345 to 236. So it's important to study the modification factor. What was the stress? 330. 330 is greater than 236. You have finite life. So if you remember, for the SN curve, for ductile material, SE is 236. So the stress that we have is 330. It's going to be larger than this. But we don't know if it's going to be on this curve or this curve. So is it high enough to go through this criteria, or it's going to be on this line? So I will finish this example during the class.